So as kind of an introduction to the derivatives of inverse functions, I have a recap for you guys on what we should know about inverses, what we should remember about them. So first of all, this first line that I have here, remember having to do with the graphs, because we're going to deal a lot with the tangent lines, which brings us to graphing and things like that. So remember that the graph of an inverse function is a reflection around that diagonal line y equals x. So you can picture like part of a square root function with part of a parabola, like something like this. Like a square root function looks like this, half of a parabola looks like this. They're reflections around that diagonal line y equals x. Hopefully you remember that about inverse functions. So consider the line 3x minus 8. We're going to work with kind of an easy example here. So what is its slope? Well, its slope equals 3. That is something that I hope you guys could have answered in Algebra 1. So the inverse of y, let's talk about that as well. So again, this is kind of a reminder of how we have to deal with inverse functions. We did this at the beginning of the year in our whole review chapter. The way that we find inverses is we literally swap the x and the y like this, like replace the y with an x, replace the x with a y. Whoops, that should be minus, not equal to, sorry. And then you do just a couple of quick algebra steps in this case to get the y to be by itself again. So we add 8 to both sides. So that gives us x plus 8 equals 3x. And then divide both sides by 3. So to get back in slope-intercept form, that would be a 1/3 x and then plus 8/3. So what is its slope? Well, the slope here is 1/3. So that's something to think about, something to notice. And normally, if we were in class and we were having a discussion, we would talk about the fact that, this function has a slope of 3, this function has a slope of 1/3. How do they relate? They're reciprocals of each other. So the inverse functions have reciprocal slopes. Just a first example to look at with linear functions. Of course, we're going to start to look at other functions where the slope is constantly changing, not a constant slope. I guess I shouldn't use the word constant when I say constantly changing. We're going to look at equations where the slope is variable compared to linear functions where the slope is constant. So if we look at something like this, x squared minus 1, the slope is variable, meaning it changes as x changes. We want to first find the derivative at x equals 1. All right, so let's start with that. So finding the derivative, y prime is equal to 2x and then minus 0, technically. The derivative of 1 is just 0. So y prime is 2x, so if we wanted to evaluate it when x equals 1, we would get 2. So the derivative at x equals 1 is 2. All right, so now find the inverse of y. That's our next thing. We want to find the inverse of y. So instead of y equals x squared plus 1, like I said, we are going to just literally swap those variables like we did on the previous page. So we're going to write x equals y squared minus 1. And so a little bit of algebra here. We are going to add the 1 to both sides. So that gives us x plus 1 equals y squared. And then we're going to take the square root. All right, so y equals, technically, I could have the positive or negative version. But if I look back here, at x equals 1, I have a positive, or I guess I have a 0 y value. So here, since I'm using a positive value of y, let me try this again. Here, since I'm using a positive value of x, the x's and y's all swap. So a positive value of x here means I want to choose the positive value of y here. Because again, the inverses swap. X's become y's, y's become x's. So the fact that I had the positive version of x on my original function means I choose just the positive version of y for my inverse function. Because really a square root function is only half of a parabola, so you're really only choosing half of that parabola to work with. All right, so now we're going to slowly work our way through this. So if 1, 0 is a point on the graph of y, what point can be found on the graph of y inverse? So we should know this. The x and y points all just swap. So if 1, 0 is a point on y, what can be found on y inverse? Well, 0, 1. Just swap the x with the y and we get a new point, which is true. 1, 0 is definitely a point on this graph. If I plug in 1 for x, I get 0 for y. And then again, the point 0, 1 is definitely on this graph, the inverse. If I plug in 0 for x, I get 1 for y. So let's, just to give you a little visual, to give you a little sketch. So my original function, square root of x minus 1, I go down here, and it's a parabola that looks something like that. And then the square root of x minus 1, remember the minus 1 means that I move to the left. So this function is going to move to the left 1 unit, and then it's going to look something like this. So really, the only two pieces that I'm looking at, like I look at this entire piece, that's the square root function, I'm only looking at this right-hand piece as being the original function, because I really only flipped this one piece over the line y equals x. So the 2 points that I was just talking about, the point 1, 0 is right there on my original function, which means that the point 0, 1 is a point on my inverse function. And so those are reciprocals of each other around the line y equals x. Just that nice little mirror image point. All right, so now find the derivative of y inverse. Well, y inverse equals the square root of x plus 1. So when I take the derivative of that, first thing I'd like to point out is that this is horribly clumsy looking notation, but we're going to do it anyways. In order to write y inverse prime, I have to put the y inverse in parentheses and then put prime like that on the outside. It's awful. Basically all I have is like 3 little dashes. One of them is horizontal and it means negative. One of them is vertical and it means 1. One of them is diagonal and it means derivative. So I have y inverse prime. When I take the derivative of this, I've technically got a little bit of a chain rule going on. So this is x plus 1 to the 1/2 power. Remember that, so I can use a power rule. So the derivative rule says that my 1/2 comes out front, the power drops down to a negative 1/2. Do not forget that my nested function stays exactly where it was. And then I multiply by the derivative of the nested function. That's a linear function, so the derivative is technically just 1. Okay, so that's the derivative. There it is right there. And it said find the derivative at this point. This point, the one that we just answered. So then we want the derivative at the point 0, 1. So let me rewrite this function. This is 1 over 2 times the square root of x plus 1. So if I want to know the derivative at x equals 0, I could just plug the 0 right in. So I would have 1 over 2 times the square root of 0 plus 1. Well, 0 plus 1 is 1. The square root of 1 is 1. So this is actually just 1/2. Okay, so again, something to think about. We talked about 2 different inverse functions and what their slopes look like at one particular point. So let's kind of backtrack what we've discovered so far. Here you've got an original linear function. Its slope is 3. You took its inverse. The inverse slope was 1/3. We talked about how they were reciprocals of each other. But for this one, it's kind of a unique situation because it's a linear function where the slope is constant. So we worked our way into an example where the slope was variable, not constant. So we found the derivative at x equals 1 of the original function. It came out to be 2. Then, a few steps later, we found the opposite point. So the original function had a point 1, 0, which is what I just found the derivative at. The inverse function has the point 0, 1. The derivative at 0, 1 came out to be 1/2. So at these opposite points, my graphs had reciprocal slopes. So opposite points, 1, 0 compared to 0, 1, they had reciprocal slopes. At 1, 0, my original had a slope of 2. And at 0, 1, my inverse had a slope of 1/2. So that is what we are going to write down as kind of the summary of what the derivative means for the inverse. So assume that our function is differentiable and it's got an inverse that we mark by g. And so here is what we've got. So if b belongs to the domain of g, so g prime of b exists, and g prime of b is the reciprocal of f prime of a, where f of a equals b. So that means is a comma b is a point on f, which makes b comma a point on g, the inverse function. So whatever the graph slope is at a, the inverse graph at the opposite point has the reciprocal slope. A lot of this seems absolutely crazy until we have actually looked at some points. We're going to look at kind of a visual explanation here. So let me show you guys just a quick little picture. So I'm going to use just some nice easy linear functions here. So let's draw one linear function. Kind of looks like this. All right, so that will be our original linear function. So we're going to talk about two different points. Let's use the x-intercepts. We'll call that c, 0. And then we'll pick another point right here. So we'll call that a, b. All right, so I'm going to have this other point. So there's going to be a inverse point that I can graph that's at the point c, 0. So whatever this distance right here is, I mark the same distance up the y-axis, and then that will be the point 0, c. All right, so that's my first reciprocal point. And then my next point, a, b, I'm going to go a units up the y-axis. So that is about, so I'm going to go a units up the y-axis, which takes me actually right under the word and then I'm just going to go this far out. So that is unfortunately going to put me right there, right in the middle of my definition. So that is the point b, a. It is the opposite point. All right, so now if I draw a line through those 2 points, I'm going to be super careful. Okay, so here's my original function. This is my inverse function. Notice, if I did a decent job of this, that these two should be reciprocals around the line y equals x. I'm sorry, mirror images, reflections across the line y equals x. So these points are reflections of each other, right here. And then these points are reflections of each other. So this is the line y equals x. We're going to talk about why the slope thing works out the way it does. So let's talk about the slope of f. The slope of f, if we just do a quick calculation, like change in y over change in x, we have b minus 0 over a minus c. Okay, and then the slope of f prime, I'm sorry, f inverse, that should not be an f prime, that should be an f inverse. Slope of f inverse, we do the same thing. This time we have a minus c over b minus 0. So what you hopefully notice is that they are reciprocals of each other. So that is how that whole reciprocal slope thing ends up working out. So maybe that visual did something for you, maybe not. But the point to take away is that these inverse functions have reciprocal slopes when you look at their opposite points, like AB compared to BA. So let's look at this thing right here. So suppose f is an invertible function, meaning you can find the inverse, satisfying all of these things right here. So we know this, we know this. If g is the inverse, we want to find g prime of 2. Okay, so g of 2, here's what we can write down, like this thing right here. G of 2 is the reciprocal of let me go right here. F prime of A. Here's the problem though, is I don't know what that is. It's like f prime of something. And then we look to our last piece. So where f of A equals B. So where f of something equals 2. Okay, so I just kind of copied that sentence down so I know where I'm looking for the derivative of my inverse function. So that's how I figured out that should be playing B in this sentence right here. So g prime of 2 is the reciprocal of f prime of something where f of something equals 2. So now back to what I know. Well, I know what that something is now because they gave me this bit of information. F of what equals 2? F of 3. So that means this is a 3, this is a 3. Okay, so that's what I figured out so far. G prime of 2 is the reciprocal of f prime of 3. So I know that this is true. F of 3 equals 2. They just handed that to me. And if I want g prime of 2, it's just the reciprocal of f prime of 3. So since f prime of 3 is negative 4, that means that g prime of 2 is the reciprocal, which is a negative 1/4. So there's really not that much to it. All right, so now the other one. Calculate g prime of x for f of x equals 4x cubed minus 1. So what I need to do is I need to take the inverse, and then I can find the derivative. So if I swap, I do x equals 4y cubed minus 1, add 1 to both sides, divide both sides by 4, and then I can take the cube root. All right, so y equals the cube root of x plus 1 over 4. All right, so what I'm going to do to take the derivative of that is I am going to, I kind of got a chain rule, quotient rule sort of thing going on. All right, so I'm going to write this, first of all, kind of as a linear function, like 1/4 x plus 1/4. That should help us, because you don't really need to do a quotient rule, so I don't want you to trick yourself into thinking you need to do a quotient rule. So y prime. Chain rule, this cube root, remember, is really the 1/3 power. So the 1/3 comes out front. My power drops down to a negative 2/3. And then I multiply by the derivative of the nested function. So now hopefully you're glad that I wrote the nested function out as a linear, because then you know pretty quickly that the derivative is a 1/4. All right, so if I simplify this, I get 1/12 from the 1/3 and the 1/4, and then times this quantity raised to the negative 2/3. Now, if you don't like the negative 2/3 and you want to flip it to the denominator, or you want to write it as the cubed root of something squared, feel free, but I think this is probably far enough for us to just leave it. All right, so we've got a little bit more to work through here. So find g prime of 1/2 if g is the inverse of f of x. So again, do not try to find an inverse formula. So let's copy down that sentence that we had on the front. So g prime of b, so that means g prime of 1/2, is the reciprocal of f prime of something. So our goal is first to find that something, where f of something equals 1/2. So if I want to find that something, I need to find the x value that gives me a y value of 1/2. So what I do is I take this function. It says do not try to find an inverse formula. Believe me, you are not going to want to. So let's start by setting the function, x cubed over x squared plus 1 equal to 1/2. Now, unfortunately, I don't really know another way to help you do these besides to say to just think about it. So if we try to think about what x value would give us 1/2, the only possible x value that would work would be 1, because 1 cubed gives you 1, and then 1 squared plus 1 gives you 2. So the x value that works there is 1. Like I said, there's really no way to solve that by hand, unfortunately. You could do it in your calculator if you don't really spot the 1 right away as being the answer. So this value that we just found right here means that f of 1 equals 1/2. So if we plug 1 in here, we end up with 1/2. So that is the value that we are looking for right here. So what we know is that if 1/2 is a point on the original function, that means that 1/2 1 is a point on the inverse function. So we want to find g prime of 1/2. We know that it's the reciprocal of f prime of 1. So we find f prime. Quotient rule. So low, d high, the derivative of x cubed is 3x squared, minus high, d low, the derivative of x squared plus 1 is a 2x, and then all of that over low, low. We want the derivative at 1, so don't simplify it any further than that. Just plug the 1 in. So 1 squared plus 1 is 2. 3 times 1 squared is 3. Minus 1 cubed is 1. 2 times 1 is 2. And then 1 squared plus 1, that's 2. And then we square it and we get 4. So this is 6 minus 2 over 4. that reduces down to 1. So when x equals 1, the derivative is 1. So last thing, we know what this is. So we know that this equals 1. So f prime of 1 is 1. That's what we just found here. G prime of 1/2 is the reciprocal. So what that means is that G prime of 1/2, G prime of 1/2 is the reciprocal of 1, which, is also 1. Okay, sneak this guy in here. So we've got f of x equals this function right here for x values that are less than or equal to -6. If g is the inverse, calculate g of 4 as well as g prime of 4. So let's look at that sentence one more time. So g prime of 4 is the reciprocal of f prime of something, where f of something equals 4. Okay, so just like we did up above, we know here that this is a y value for the function. So we set the function equal to that y value, and then we solve for x. Okay, first thing I do is I square both sides. And then I can subtract the 16. Then I can factor it down. So what multiplies to -16 and adds to 6? That would be a +8 and a -2. So last thing, I solve these. I get an x value of -8 and an x value of +2. So as far as I can tell, it looks like I've got two options. However, they restricted me right here for x values that are less than or equal to -6. So this is the only one that I'm interested in. So that is my value of x that gives me a y value of 4, which means that's the value that goes right here too. So if -8, 4 is a point on the original function, that means 4, -8 is a point on the inverse function. So the first thing I figured out is that g of 4 is equal to -8. That's one of the things I was supposed to be answering. If f of -8 is 4, then that means that g of 4 is equal to -8. Last thing is I need to find f prime of -8 so that I can take the reciprocal. So starting with f prime, this right here requires a chain rule. Remember, that's technically raised to the 1/2 power. So I bring the 1/2 out front. Power drops down to a -1/2. And then I multiply by the correction factor, which is the derivative of the nested function. So the derivative of x squared is 2x, and the derivative of 6x is 6. So now again, since we're only looking for the derivative at a specific points, I really don't need to simplify this up at all. I could, believe me, there are plenty of things I could do to simplify, but I'm just going to plug it right in. So -8 squared is 64, plus 6 times -8 is -48. That's raised to the -1/2. 2 times -8 is -16, plus 6. All right, so let's simplify this up some. So -16 plus 6, that's a -10. -10 times 1/2 leaves me with a -5. In here, 64 and -48, that leaves me with 16. 16 is the -1/2. That means I'm square rooting and then taking the reciprocal. So the square root of 16 is 4, so the reciprocal is 1/4. So this is 1/4 and then times a -5. So that is a -4/5. So again, that is f prime of -8. I just found the derivative of my function f and plugged in the -8. What I need also is g prime of 4. G prime of 4 is the reciprocal of f prime of -8. Well, f prime of -8 is -5/4, so that must mean that g prime of 4 is a +4/5. Oops, I'm sorry, opposite reciprocal. Not opposite reciprocal, just the regular reciprocal. So -4/5. I'm not taking the opposite reciprocal. This isn't parallel line stuff. I am just flipping numerator and denominator, and that is it. All right, so let's save this one last one to do together. Nice little AP problem. All right, so we're all set.